Hello. In this video, we are going to calculate the wavelength of a photon that is necessary to an excited electron in a one-dimensional particle in the box problem from the n equals 1 to the n equals 2 level if the box has a length of 4 angstroms. Now recall that 1 angstrom is equal to 10 to the minus 10 meters. Also recall that the energies for each level in the particle of the box is equal to, so E sub n is equal to n squared h squared divided by 8ml squared, where n is the quantum number, h is Planck's constant, m is the mass of the particle, and L is the length of the box. So what we're going to do is first compute the h squared divided by 8ml squared part. So Planck's constant is 6.626 times 10 to the minus 34 joule seconds. And that quantity being squared divided by 8. And the mass of the electron is 9.109 times 10 to the minus 31 kilograms. And since our length here is 4 angstroms, so that's 4 times 10 to the minus 10 meters, if we square that, we get 16 times 10 to the minus 20 meters squared. So this particular part of the calculation, just the h squared divided by 8ml squared, has the value of 3.766 times 10 to the minus 19 joules. Now notice, even though the problem doesn't specifically ask for it, since this corresponds to the energy when n is equal to 1, this is the ground state energy for the electron. So the next step is to calculate the difference in energy between the n equals 2 and the n equals 1 state. So since we have this n squared term in front, it's going to be proportional to h squared over 8ml squared. So we're going to have 2 squared minus 1 squared since we have n equals 2 and n equals 1. So this is equal to 3 times h squared over 8ml squared. And then we can simply compute this value by multiplying our ground state energy, 3.766 times 10 to the minus 19 joules, by 3. So this energy difference, E2 minus E1, is equal to 3 times 3.766 times 10 to the minus 19 joules. So computing that, we get that this change in energy is equal to 11.29649 times 10 to the minus 19 joules. Now also recall that the energy of a photon is equal to h times nu, where h is Planck's constant and nu is the frequency. to get the frequency from this expression, we need to divide by Planck's constant, which is 6.626 times 10 to the minus 34 joule seconds. So we can divide through by h here, divide through by h. Seconds. And this gives us that the frequency of this particular radiation is going to be 1.7049 times 10 to the 15th inverse seconds. Next, we recall that the wavelength is equal to c divided by the frequency. We know that the speed of light is 2.9979 times 10 to the 8th meters per second. And we've already calculated the frequency of the necessary radiation to be 1.7049 times 10 to the 15th inverse seconds. And we notice that we get the proper units here, since the units of the inverse seconds cancel, and we get that the wavelength is 1.75 times 10 to the minus 7 meters, which is also equal to 175 nanometers. So the necessary radiation to excite the electron from the n equals 1 to the n equals 2 levels would be provided by a photon in the ultraviolet region. Thank you very much for your attention. Have a good one.